eubiotic microbiota. But we now know, I mean, the classical teaching, if you look back just a few years ago, the dogma has been for 150 years that the fetus is sterile unless there's something wrong, that amniotic fluid is sterile, the placenta is sterile, and that acquisition of the gut microbiota only begins essentially during birth and then following birth, and that's where we get it. But this turns out to be, as so many other things that I learned over my career years ago, this turns out to not be true. And we now know that amniotic fluid is not normally sterile, that you can find small populations of bacteria, and all of these different genera are listed here on the right of the slide. As you look at it, you can find Enterococcus, Staphylococcus, Streptococcus, Klebsiella, Bacteroides, Bifidobacterium. All of these can be found in the amniotic fluid. And then, of course, because the fetus is drinking the amniotic fluid during development, these then inoculate the meconium. We also know that the placenta now harbors its own microbiome that is involved with protecting the fetuses, and if there's something wrong with that, maybe associating, if there's a dysbiosis of the placental microbiota, this is associated with preterm deliveries, especially preterm deliveries before 28 weeks. So the microbiota occurs before birth, starts to occur before birth, but really takes off after birth. So the baby, as it's being born, is covered with the microbiota of the cervix, of the vagina, and of the perineum. And then there's great homology between the organisms you can find. For example, E. coli serotypes in the nasopharynx of an infant after birth. That's going to match up perfectly with E. coli found in the mother species, for example. A lot of these Streptococcus and Enterobacteriaceae organisms are aerophilic, and they get into the intestines. They're swallowed by the baby, and they grow, and they essentially set up the anaerobic environment that's required for bifidobacteria and Bacteroides and various Clostridia clusters. And so you get an establishment of this predominantly anaerobic flora that occurs, within the first week of life. And then if the baby is breastfed, the baby develops a Bifidobacterium predominant microbiota, and that's normal. And babies who are not breastfed don't develop a normal Bifidobacteria predominant microbiota, and that has health consequences for them. And babies that are born by cesarean section don't develop, they have a dysbiotic microbiota because they haven't had that initial exposure. And of course, the worst thing is to be born by C-section and be formula fed and to spend a lot of time in the hospital, and those poor infants don't develop anything close to a normal microbiota. But there is this microbiota that develops during infancy and becomes more adult-like after weaning and exposure to solid foods. And you have a predominance of the Firmicutes, the gram-positives, which include things like Lactobacillus, Clostridium, Bifidobacterium. I'm sorry, not Bifidobacterium, but Lactobacillus and Clostridium, and Eubacterium, and then you have the Bacteroides, and these become more predominant as one is older, and you have a decrease in Bifidobacterium as one ages. And there are many people that speculate that this decline in Bifidobacterium numbers with age contributes to immune dysfunction in the elderly. If all goes well, you come up with a balanced, eubiotic microecosystem that keeps potentially harmful bacteria in check, like Pseudomonas or Proteus or Staph, and has good numbers of potentially helpful bacteria, which of course are modulating your immune function, are aiding in the digestion and absorption of nutrients, stimulating gut motility, synthesizing vitamins, and inhibiting pathogens and potential pathogens. It's a complicated place. This is a complicated slide, but it's just to really illustrate two things. One is that everybody's microbiota is a little different. So we may have similar organisms, but the balance is going to be different from person to person. So, for example, here's a healthy 28-year-old woman on the upper left, and she's got over 20% bifidobacteriales. So she's got a really healthy bifidobacteria population, and that's a good thing. And then here's this 37-year-old down around 5%. And so he's got much more in terms of Clostridia and studies published years ago in Nature suggested that humans were beyond loyalty predominant, or chromosomal predominant, or bacteroides predominant population. Based on much of Western population. Extrapolate this to the whole world. There might be some additional larger studies intended to suggest that healthy people do break down into different anotypes. Probably a lot of this is based on diet. But everybody's not the same, and so the approach to dysbiosis isn't going to necessarily be the same in everybody. Just keep that in mind. The gut microbiota, one of the most important things that it does is to maintain intestinal integrity. And specifically, when we're talking about intestinal integrity, one of the things that encompasses is healthy barrier function. So you don't have a leaky gut. You have good gut barrier function. The integrity of the intestinal barrier is maintained intact, so you're only absorbing things that you need to absorb, and other things like toxins or pathogens are not coming into your body. The commensal bacteria helps with this because it stimulates mucus production. Mucus is obviously an important protective barrier. We know, for example, that people with inflammatory bowel disease have less thick mucus than people with healthy guts. The commensal bacteria stimulate the enterocytes of the cells lining the intestine to secrete defensins. These are molecules that, as the name suggests, defend the body against pathogens. They have toxic effects on pathogens. The commensal bacteria produce microcins or bacteriocins. You'll see it referred to. These are molecules with toxic effects on pathogens, and part of the way that the commensal bacteria keeps pathogens in check keeps them from translating across the mucosal barrier, the gut barrier, into the submucosal areas and regional lymph nodes. And one of the most important things that the commensal bacteria do is modulate immune function, and they do this primarily by increasing activity of regulatory T cells. And here's an illustration of this. People used to talk about how you had naive T cells. These would be the Th0 cells, and then these T cells could differentiate into helper 1 T cells, Th1 T cells, and these were responsible for cell-mediated immunity, or they could differentiate into helper T cell 2s or Th2 T cells, and these were associated with humoral immunity, and overexpression of Th1 cells was with tumor necrosis factor and interferon gamma, and interleukin-2 was associated with autoimmune diseases if it was overexpressed, while overexpression of Th2 T cells with various interleukins 4, 5, and 10 was associated with allergies. So people used to talk about a Th1 to Th2 ratio, and if you have too much Th1, you need to balance it by increasing Th2. And that turns out to be completely wrong. And the important ratio is between regulatory T cells, the Tregs, and the effector T cells. So all these other T cells. And in addition to Th1 and Th2, there are also other helper T cells. Th17 is associated with cellular immunity, and so is Th22, just as Th9 is associated with asthma. And it turns out these cells are not even terminally differentiated. So a Th2 cell can turn into a Th1 cell, or a T regulatory cell that should normally damp down excessive immune responses can turn into a Th1 or Th17 cell. What's important is that it are robust populations of T regulatory cells, and that's where the gut microbiota and that's where probiotics play a major role in regulating and modulating immune function. So how do we modulate the gut microbiome? We've got 5 different modalities, general big modalities that we can use to modulate the gut biome, and I'm only going to talk about 2 of them, but I want you to know about all of them. One is diet, and this is probably much neglected, and it's something I could spend another hour or a couple hours on talking about diet. But we shouldn't forget about diet, and it almost strikes me as pointless to take probiotics or take immune fiber and have a diet of junk food. I mean, it's like, what are you trying to do? So if you don't address the diet, and if you don't clean up the diet, and if you don't encourage the intake of a lot of soluble, for us, undigestible fiber and fresh fruits and vegetables and legumes, then it's going to be hard to really make an impact with other modalities like probiotics and prebiotics. You can also modulate the gut flora with antibiotics, and so, for example, what you'll immediately appreciate, for example, antibiotic therapy, rifaximin of small intestinal bacterial overgrowth. What are we doing? We're trying to modulate the gut microbiota. We're trying to decrease populations. There's a whole literature on antibiotics and Crohn's disease. So the problem with antibiotics is how do we know that we're just killing things, the bad organisms that are responsible for diseases? And you have the drug with really limited spectrum, like rifaximin, that doesn't appear to harm healthy commensal bacteria, or you have other antibiotics that are potentially more toxic. But this is a way of modulating the microbiota. And then finally, you have fecal transplantation, again, way beyond the scope of this presentation, but a very exciting area. Obviously, what's available to us as probiotics is really limited in terms of the actual populations composed in the healthy gut. Fecal transplantation allows you to transplant what you hope, you do your best to document, is a healthy microbiota from a donor into somebody's significant problem, like recurrent Clostridium difficile disease, which is obviously a potentially fatal disease, or it's even being done in inflammatory bowel diseases with some success. And in this country, anyway, the FDA says that it's regulating this and it's experimental, but it's very exciting. So in terms of definitions, probiotics, the term was first used in 1965, and what it referred to was microbially produced, so growth factors produced by microbes that promote good microbes, basically. And so Fuller in 1989 expanded that to say that these were live microbial feed supplements. So we should all know that really where probiotics are extensively used and have great impact, especially as an alternative to antibiotics, is in animal husbandry and is in raising chickens and pigs. And so there's a lot of work that goes on in that, and that's where probiotics as live microbial feed supplements that benefited the host. That's where the concept was really developed, and then it was sort of ported over to humans. And a currently accepted definition of probiotics is these are viable microbial food supplements that have a beneficial influence on human health. So so a couple things. It has to be microbes. They have to be viable. They can't be dead. It's going to be a probiotic. And they have to have a health benefit, sort of by definition. If there's no health benefit, it's not a probiotic. Now, prebiotics are non-digestible substances, the substances that we don't have the enzymes to digest, that stimulate the growth and or activity of selected GI microbes. So it doesn't mean that you have to increase populations of certain beneficial microbes. You just have to increase their activity. And in fact, there are many people, there's this concept of functional dysbiosis. So there may not be something on a stool test that really that jumps out at you in terms of too much of this or too little of that. But functionally, in terms of what sorts of enzyme activities and what sorts of nutrients are being produced, that might be where the dysbiosis is. And so that could be moderated by prebiotics. And then symbiotics is a combination of probiotics and prebiotics. That's all symbiotic is. So it's just a brief history of probiotics. I like the concept of essential probiotics, like essential vitamins. We have evolved with these organisms. And in fact, there's a great paper in Nature this past month looking at humans and their nearest relatives, chimpanzees and gorillas. And we have evolved with similar firmicutes and similar Bacteroidetes and other organisms. However, in terms of species differentiation, we've all had our own microbiota as humans different from other primates for 15 million years. And we get them from our environment, and we get them from our mothers to begin with, and then we get continual exposure to them as we take in probiotic organisms from our diet. And we find probiotic organisms naturally on fruits and vegetables, and I'm sure that humans discovered thousands and thousands of years ago natural fermentation of different fruits and vegetables and appreciated them. And we know that 10,000 years ago that people started fermenting beverages on purpose. And in fact, there's one whole theory about the origin of agriculture that had nothing to do with assuring a good supply of food, a reliable supply of food, and had everything to do with securing a reliable supply of beer. We know that yogurt was developed about 3,000 years ago. Basically, fermented foods have been part of the human fabric for a long time. And Hippocrates, of course, the father of medicine, prescribed sour milk and realized that there was therapeutic benefit in giving patients with GI disorders sour milk. Pliny the Elder also expounded on the benefits of sour milk, and in fact, Francis I of France, was cured at the time was allied with the Sultan of Turkey, and your complicated European politics, and was sick, gastroenteritis, and was cured by the Turkish physician, cured of dysentery by yogurt. So the godfather of probiotics is Eli Mechnikov, who won the Nobel Prize in 1908, not for probiotics, but for the description of phagocytosis. But he was the first person to really draw. He worked at the Pasteur Institute, and he was quite aware of microbes. And he was the one that understood that taking in fermented foods like yogurt made possible the prolongation of a healthy life. And he wrote this in his seminal work, Prolongation of Life, which was published just about 110 years ago. So the types of probiotics, most of the probiotics that are available to us are organisms that have been used in food and beverage production. So keep that in mind. That's why we have these. That's why the FDA lets these get on the market. Is that there has been a lot of experience, in many cases thousands of years of experience with these organisms. So they're generally divided into lactic acid bacteria, lactobacillus species. Of course, some people would quibble about whether the bifidobacterium species should, strictly speaking, be called lactic acid bacteria. Acetate is a more preferred end product for them. But many people lump them in. Streptococcus pneumophilis, this is a traditional yogurt starter, highly adapted Streptococcus, non-pathogenic. Enterococcus faecium, Lactococcus, Laconostoc, Pediococcus. These are all organisms that produce large amounts of lactic acid. Then there are the non-lactic acid bacteria. There's the Bacillus species. These are often referred to as soil-based organisms. There's the Propionibacterium species, and there's E. coli nissla. It's a specific strain of E. coli isolated from a German soldier in 1917. Everyone else in the unit died of dysentery. He survived, and the German physician assumed that it was probably because of his microbiota and isolated this particular E. coli. This is available, and there's some good evidence that it's beneficial in Crohn's disease, for example. And then the non-pathogenic yeast, Saccharomyces boulardii. Lactobacillus characteristics, these are gram-positive rods. They can also have a coccobacillary form. They don't make spores. Broadly divided into homofermentated, so 85% plus of their fermentation end product is lactic acid, or they're heterofermentated, so in addition to lactic acid, they also make carbon dioxide, ethanol, and acetic acid. They digest and metabolize proteins and carbohydrates, make B vitamins, vitamin K, they break down bile salts. They're intimately involved with modulating immune function, and they inhibit a variety of pro-inflammatory mediators. Clinical studies and animal studies over the years have shown that lactobacilli have active antimicrobial properties against a wide variety of pathogens, gram-positives, gram-negatives, and yeast. This is a list of probiotic lactobacilli that are generally available. I'm only going to discuss a few of them in detail. Lactobacillus acidophilus, this is the prototypic probiotic. So if anybody's ever heard of a probiotic, what they've heard of is Lactobacillus acidophilus. It's important to realize that a lot of strains that 20 years ago were classified as Lactobacillus acidophilus have since been reclassified, so that can be a little confusing when you look at the literature. Currently, it's thought that Lactobacillus acidophilus is a transient species, meaning that it's only going to be there if you're taking it in your diet. A lot of what used to be classified as endogenous Lactobacillus acidophilus has now been reclassified as like Lactobacillus salivarius or Lactobacillus gasseri. Lactobacillus is an obligate homofermentated organism. It never switches to heterofermentated. It has to make a lot of lactate, and it makes both isomers of lactic acid. It's very hardy, resistant to acid, bile, pepsin, pancreatin. It has over 20 known peptidases, and it has been shown to break down both casein and gluten, which are problematic polypeptides. Ferments lactose, and in fact, there's a literature on Lactobacillus acidophilus for lactose intolerance. And it can reduce gut concentrations of various carcinogenic enzymes, although the studies that yet to be done that show that probiotics can reduce the risk of colon cancer. Lactobacillus rhamnosus, this is probably the most studied probiotic. It's relatively fragile. It's much more susceptible to stomach acid. So it's generally transient, although people can isolate it in the gut. It's a heterofermentated, and it only makes the L-positive lactate isomer. It's got great colonic mucosal adherence, although that's done in vitro, and how relevant that is to in vivo, we don't know. It makes more peptidases than any other lactobacillus, and it enhances innate and acquired immunity. It antagonizes various pathogens like rotavirus, C. difficile, and E. coli. Lactobacillus casei is another adaptive probiotic closely related to rhamnosus, again, transient species. And one of the things that this has is a large number of proline-specific peptidases, and these are particularly useful in breaking down casein and gluten, because these are polypeptides that have a lot of proline in them. It also makes the L-positive and only the L-positive form of lactic acid. And although it's transient, it's interesting in that its presence is required for differentiation, for normal differentiation of dendritic cells. So it's amazing. So you require this transient species for normal immune maturation. Lactobacillus plantarum, this is ubiquitous on plants. That's why there's a picture of vegetables here. Generally lacking in modern diet. So if you do stool cultures from people in Africa who are eating a traditional diet with a lot of fiber and legumes, they all have Lactobacillus plantarum. And humans have modern Western diet. People consuming modern Western diets have like 25% of them have Lactobacillus plantarum if they're not taking it as a probiotic. Very hardy organism, resistant to bile and acid. It facilitates induction of IL-10. This is really important for T-cell regulatory function and decreasing both allergies and inflammation. And it strongly supports intestinal barrier function and reduces translocation of gut flora. Now, Bifidobacterium, these are the second major class of probiotics, gram-positive. They don't make rods. They often have a Y shape to them, especially when they're stressed. That's why they're called Bifidobacterium. They're strictly anaerobic and fastidious. The one exception there is Bifidobacterium lactis. They have a unique metabolic hexose pathway called the bifidus shunt. They all break down lactose. They ferment a variety of non-digestible oligosaccharides. And they synthesize B vitamins, vitamin K. Again, they're intimately involved with modulation of both innate and acquired immunity, and inhibit a variety of pro-inflammatory mediators, and inhibit a variety of different pathogens. And when you look at different disorders and disease states, what you will see over and over again is that disease or ill health is associated with reduced bifidobacterium populations, and robust bifidobacterium populations are associated with gut health and immune health. These are the major bifidobacterium probiotics. And we'll discuss some of them in a little more detail. So Bifidobacterium longum, this is often, so if you're fortunate enough to have a dominant Bifidobacterium microbiota, it's usually going to be the Bifidobacterium longum that's dominant. It ferments a variety